Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where I am trying to help you to achieve the dream 60 out of 60 in your KCET 2025 in physics subject. Now we have discussed all the chapters of your second PU, and today we are going to conclude the chapter discussion of semiconductor and electronics, and tomorrow we will complete the PYQ. So your second PU entire syllabus will be over by tomorrow, and day after tomorrow, as you know, Sunday, we will be back with KPL, that is KCET Premier League, where I will give you 30 questions to answer, and once you answer that at night, I will be back with the solutions, that is on Sunday. Now, how you can get that question paper, how you will be able to get that question paper, for that you have to join our WhatsApp channel. The question paper link will be provided absolutely free of cost. Just only thing that you have to do is install your WhatsApp. If you don't have, open the WhatsApp and then click on the link given below on our YouTube channel, and from there you will be redirected to WhatsApp, and there you have to click on the follow button. Then you will be able to follow our channel, and whenever we are posting a new video, any update related to KCET 2025 exam, you will be get that update, and that is the main requirement to get the KCET KPL question paper. So now we will be continuing with this chapter. Also, those who are wondering what will be the syllabus for this week's KPL, as I mentioned, nuclei and semiconductor electronics will be the chapter for this week's KPL. I hope you have prepared these two chapters well. Let's start with the list of content that we are going to discuss today. We will discuss P-N junction, obviously very important. Then we will discuss semiconductor diode. Then we will discuss what is forward bias diode. Then we will discuss what is reverse bias diode. Also briefly we will discuss IV characteristic of a diode. Then diode as a rectifier. Okay, not the detail of a diode as a rectifier, but a basic principle of diode as a rectifier. Then we will conclude this chapter. Now let us discuss about P-N junction. So yesterday we have discussed about P-type semiconductor and N-type semiconductor. Okay, now what is then P-N junction? P-N junction is the basic building block of many semiconductor devices. Okay, for example, diodes, transistors, etc. Okay, P-N junction is a common thing. Okay, it is available in diode, it is available in transistor. Transistor is no longer part of the syllabus. It was deleted long back, even before pandemic it was deleted. So don't worry about the thing transistor, but diodes are there in your syllabus. So let's see what is a P-N junction diode. Now, how a P-N junction is formed? Very important. Consider a thin P-type silicon semiconductor wafer. Semiconductor wafer means basically, if you see semiconductors comes like a if you have seen the compact disc CD. Okay, so that is our whatever semiconductors that we synthesize, they come like a CD like structure. Okay, or it is a thin structure. Okay, very thin, as thin as CD, and mostly circular, but in some cases for particular manufacturer it can be like a biscuit as well, but it will be very, very thin. Okay, so that is what we are calling as semiconductor wafer. Okay, wafer, you eat wafer, right? So there are multiple layers of wafers that you eat. Okay, so this is a single layer of that wafer. Okay, by adding precisely a small quantity of pentavalent impurity, a part of the P-type silicon wafer can be converted into N-type silicon. So what is that? We have a base. We have a base where part of it was P-type silicon, and we have induced some N-type silicon as well. It is happening on a single piece of wafer. So to form a P-N junction, we have to make sure that everything is happening on a single piece of silicon. Okay, you cannot make one N-type silicon and one P-type silicon and then you cannot join them to obtain a P-N junction. Okay, to obtain a PN junction, it has to happen on a single piece of silicon. Very important thing. Okay, it is little bit related to synthesis of the PN junction, but you should remember that sometimes they might ask you a question based on this concept, that why a P and a N taking together, joining them, will it form a diode? Yes or no? Maybe in your PU board, but this is also an important concept. You cannot take a P type and N type and join them to get a PN junction. Okay, there are some problems in that. Okay, the wafer now contains P region and N region and a metallurgical junction between P and N region. So now we have one P region, this is the P region, okay, and one N region, this is the N region, and where these two junctions, these two type of semiconductor meets, this is called PN junction. This is the PN junction. Okay, so where these two meets, this is called PN junction. Okay, now two important processes occur during the formation of PN junction. First is diffusion, second is drift. Very important, we need to learn about diffusion and drift when it is happening, when you are forming a PN junction. Okay, we know that in an N-type semiconductor, the concentration of N-type semiconductor, the concentration of electrons is more than compared to the concentration of holes. Okay, so concentration of electrons is more compared to concentration of holes, obviously in an N-type semiconductor. Similarly, in a P-type semiconductor, the concentration of holes is more than the concentration of electrons. This is also true, right? So now what will happen when we are mixing them together? Now P and N both are forming on a single crystal. Individually, in a single N-type semiconductor, electrons are more. In a single P-type semiconductor, holes are more. But when you combine in a single wafer, now you are forming N-type in one side and P-type in another side. Then what will happen? Okay, during the formation of PN junction and due to the concentration gradient means, so if you consider the PN junction, okay, suppose now I am drawing the PN junction like this. In this side, more holes. So you can say this is more having more free positive charges. Okay, even though the total charge of a PN junction diode is 0. You should remember in our previous class also you have learned that total charge in a P-type is 0, total charge in N-type is 0, total charge in PN junction is also 0. Okay, but relatively there are more free holes available in one side, and here relatively more electrons are available. So there is a gradient, okay, gradient of carrier concentration. Because of the gradient, what will happen? Across P and N side, holes diffuse from P side to N side. So holes will try to diffuse from this side to this side, okay, and electrons diffuse from N side to P side. So electrons will try to go to this side. Okay, because we know that opposite charges attract each other, right? So positively charged holes will move towards the negatively charged N side. Similarly, negatively charged electrons will move towards the P side, right? But remember that here, even though I am saying positively charged holes, only thing that is moving is basically the electrons. I explained the process that holes move via capturing electrons, right? So it will capture one electron from the neighboring atom and there will be a new holes. So even though I am saying positively charged holes, only thing that can move inside any conductor, any semiconductor is electrons, okay? Even though there are holes, holes are not any particles, they are not real particles, they are just lack of electrons. So you should remember this is important for your objective questions. Okay, this motion of charge carrier gives rise to diffusion current. Diffusion current means when one side has more, another side has less. So I want that side, so I am getting attracted, I was getting attracted towards the positive side because I am a negatively charged electron, and similarly someone is positively charged holes getting attracted towards my side. So this is a mixing, right? This is called diffusion. Okay, diffusion is something different than drift. Okay, drift is when there is an electric field present, right? We remember in current electricity, if there is an electric field present, then electron slowly moves opposite to the applied electric field. That is called drift. And diffusion is when there are different charges present, okay, because one side is has more extra holes, one side has more extra electrons, so electrons will try to move towards the hole side and holes will try to move towards the electron side, okay. Now, when an electron diffuses from N to P, it leaves behind an ionized donor on N side. So normally they are neutral, right? Now when electron moves from N side to P side, what happens is that in that N side region, okay, the actual pentavalent phosphorus, which will be now left with a extra positive charge, because electrons from this side has moved to the hole side, right? Similarly, when a hole moves from positive to negative side, what happens? It leaves a negatively charged ionized core, right? The core is ionized, right? In case of N-type, phosphorus is ionized, that remains as positive. Similarly, in case of P-type, aluminium, suppose I am doping aluminium, then aluminium will be left with the extra negative charge because it has one extra electron it acquired via capturing one electron from the neighboring atom, right? As the electrons continue to diffuse from N to P, a layer of positive charge on the inside of the junction is developed. I will explain that in a while. So, if you see, this was our N side, this was our P side, okay, and all the electrons from this side diffuse to this side. Now, as these electrons are diffusing, okay, as these electrons are diffusing, you can see there is a layer of positively charged cores are left. So these are basically positively charged phosphorus, okay, and the electrons associated with these phosphoruses now move to the P side. Similarly, when holes moved from this side to this side, what happens is that, or suppose they have captured one electron from this side, so there will be some negatively charged aluminium is left, okay. So electrons are diffusing in this side, holes are diffusing in this side, and when this is happening, there is a so there is a layer of negative charge is forming on the P side and layer of positive charge is forming on N side. So this is very interesting because normally N side has more number of electrons, but after the mixing is over, okay, now there are some positive charges and there are some negative charges. So you can imagine this thing is like a war, okay. So one side is N, another side is P. They are fighting with each other. Okay, they are fighting with each other. One is throwing shots towards the other side, and they are fighting, throwing arrows towards the other. Okay, so they are fighting, and when the fight is over, okay, there are a lot of dead bodies in between. So these are the dead bodies. Okay, so someone is left with positive, someone is left with negative, so there are a lot of dead bodies in between the war field. Okay, so again we can revive them. There is a way to revive them, we'll see that. But once the war is over, everyone, this positive side is saying don't go to that side. So this positive now is preventing any more charges from moving from N side to P side. Similarly, this negative charge is negatively charged cores are preventing any holes to further move from P side to N side. So after some time this process is stopped. So once the diffusion is done, so initially for few seconds they will mix. After the mix is over, they will stop and they will no longer allow any current to pass from this side to this side, any charges to flow from this side to this side. So diffusion current will be zero soon. Okay. Now, similarly, when a hole is diffuses from P to N side, the concentration gradient leaves behind ionized acceptor level or negatively charged, which is immobile. So they are basically going immobile. Initially they are mobile because electrons and holes are moving, but after some time everyone stops moving and it becomes immobile. As the holes continue to diffuse, a layer of negative charge on the P side, the junction is developed, as I said. Now, the space charge region on either side of the junction together is known as depletion region. Why? Because all the charges in that region are now depleted. Okay, they are gone. So electrons from N side move towards P side and they combined with the hole Okay, there is a combination happening. So electrons from N side move towards P side, they combined and they formed a negatively charged core. Similarly, holes from P side move towards N side and they captured one electron, and now they are silent. They are now positively charged layer, right? So they have stopped. As the electrons and holes taking part in the initial movement across the junction depleted the region of its free charge. So depleted means gone. Everything is gone. Okay, so all the charges, that is mobile carriers, mobile charges which are able to move from P side to N side, N side to P side, they are no longer able to move. All the free charges are gone. So that is why it is called a depleted region. Okay, depleted region, depletion region. There are different names. Okay. The thickness of depletion region is of the order of 1/10 of a micrometer. So very thin. Obviously micrometer is 10 to the power of minus 6, right? It is 1/10 of that. So basically it is 10 to the power of minus 7 meter. Okay, so which is a very small distance. You will not be able to measure it without using a microscope, right? Due to the positive space charge region on the side of the junction and negative space charge on the region of P side of the junction, an electric field directed from positive charge towards the negative charge develops. So now we have static charges. Okay, one is positive, one is negative. So what will happen? Obviously, if there are two charges, one is positive, one is negative, there will be an electric field. Now what will be the direction of electric field? Electric field will be from the positive charge towards the negative charge. That is from N side to P side. Very important, because these are very opposite to that of what we generally study. So that is why they are very candidate questions for conceptual question for your KCET 2025. Very important. Okay, they have not yet come, so there is a high chance that the questions from these concepts, one of such questions will come definitely. Okay, so what is the direction of electric field in a P-N junction? So you should remember, even though P side has holes, N side has electrons, you should remember after the junction is over, the N side has now extra positive charged cores and P side has now extra negatively charged core. So the direction of electric field will be from N side to P side. Now, due to this field, an electron on P side of the junction moves to the N side and a hole on the N side of the junction moves to the P side. Now what is happening? Now reverse is happening. So initially electrons from N side moved to hole side, that is P side. Now after the depletion region is formed, now what is happening? The N side, which has a positive charge, it will try to attract whatever electrons are there in the P side, P region. Okay, and whatever P side, they will try to attract holes from the N side. So they will say, okay, you are in the N side, you are in the wrong side, come to me. Okay, and similarly P side will say, you are at the wrong side, come towards me. So they will try to attract their friends which are stuck in the other side, right? Now the motion of charge carriers due to the electric field is called drift. As we know that any motion of charges, when there is an electric field is involved, that is called drift current, right? So this is the drift. So diffusion is when at the beginning of the process, when they are mixing freely, that is called diffusion. Okay, because of the gradient of the charge distribution. When the charge distribution is different, there is a mixing, that is called drift. But when there is an electric field is involved, then that is called drift. Okay. Thus a drift current which is opposite to the direction of the diffusion current starts. Okay. Now, so if you see the same diagram, now electrons are diffusing from this side to this side. Okay, but electrons drift from P side to N side. This is also very potential candidate question. Okay, what is the direction of drift current? What is the direction of diffusion current? So these questions can come. Okay. And see, if you see, this is the depletion region. Holes diffuse from P side to N side, that is the normal diffusion, and holes drift from N side to P side, which is very important. Drift is important. In my opinion, there may be one question coming from this concept of drift. So be ready. Okay, so once the depletion region is formed, what happens is that there is a extra potential is formed. Okay, as you can see, if you consider this is to be zero potential, okay, this side has negative charge, that is below zero potential, and this side has a positive charge, so it will have a positive potential, right? Q by R, that is the potential. So here there is a difference in potential is created at this junction. Okay, this is called depletion potential. We'll see that in a while. Okay, initially diffusion current is large and drift current is small. As I said, initially at the beginning of the process, diffusion current is large because they have to develop one P-N junction. So initially diffusion current is high but drift current is low, but as the diffusion process continues, the space charge region on the either side of the junction extend, thus increasing the electric field strength and increase the drift current. Okay, this process continues until the diffusion current equals to the drift current. Very important concept. At equilibrium, whatever electrons are going from this side to this side as diffusion, at the same time same number of electron is coming from p side to n side as drift. So when this is achieved, this is called the equilibrium position. At equilibrium, the charges which are being exchanged, suppose 10 electrons jump from this side to this side. Okay, similarly 10 electrons will come from this side to this side, as well as holes. I am just giving you an example of electrons. Holes will also be exchanged in the same way. Okay, so drift current and diffusion current will be same. In a P-N junction under equilibrium, there is no net current, so net current will be zero. As I said, there will be a potential difference will be developed. Okay, that is called depletion potential. Okay, and or bandwidth. Okay, this sometimes is called bandwidth as well. Okay. Now, let us see one question that came in your KCET exam, that in N-type semiconductor, oh, that is homework question, sorry, my mistake. Let us solve the homework question from yesterday's class. In N-type semiconductor, electrons are majority charge carriers, but it does not show any negative charge. Okay, so in N-type semiconductor, electrons are majority charge carriers, right? We know that. But it does not show any negative charge. It does not show any negative charge. They are basically neutral. The reason is, okay, mobility of electrons is extremely small. No. Electrons are stationary. Obviously, no. Atom is electrically neutral. Electrons neutralize the holes. So, obviously, the main reason is atoms are electrically neutral. So, that is the correct answer. Okay, electrons neutralize holes, okay, but normally in an N-type extra electrons are there, so they cannot neutralize all the holes, right? So for any object to be electrically neutral, because atoms are by definition, by property, they are electrically neutral, so atoms are neutral. So even if you rearrange the electrons, you make some electrons free by tricking them, that is still they are electrically neutral because number of protons and number of electrons are same. Right? Only thing that you have done, you have made some electrons free so that it can conduct electricity. Right? Now, next question, another important interesting question. The upper level of valence band and lower level of conduction band overlap in the case of. So, upper level of valence band and lower level of conduction band, they overlap in case of a conductor or a metal. Right? So, in this given option, only one metal is given, that is copper. Okay. Silicon is a semiconductor, so there is a gap less than 3 electron volt. We have learned that the gap for silicon is 1.1 electron volt. So, they are not touching. If they are touching, the gap will be 0. Right? So, carbon is an insulator. Normally, there are few forms of carbon. They are allotropes of carbon. They have conductivity, but other than that, normally carbon as a element, they don't have any conductivity. So this is also not possible. Germanium is also a semiconductor, 0.71 electron volt, but copper is a conductor. So they should have their upper level of copper, upper level of valence band and lower level of conduction band should overlap for copper. Right? A semiconductor diode. Now let us discuss about semiconductor diode. What is a diode? So we have learned about P-N junction. Now we are discussing about diode. So in the first part we have learned that P-N junction is essential building block for diode as well as transistor. Now we are talking about diode. So a semiconductor diode is basically a P-N junction with a metallic contacts provided in the ends of the application of an external voltage. Okay, so what is the thing is, now we have constructed the wafer, now you have attached electrical contacts. Okay, so there are some certain ways. Okay, synthesis of p-n junction is not part of the syllabus, how it is formed, even how the diode is formed, that is also not part of the syllabus, but there are ways so that you can attach two ends to that p-n junction. Okay, so previously when we are seeing p-n junction, only the core was seen. Now if we attach metallic contact, okay, now it will become a p-n junction diode. Okay, and the symbol for p-n junction diode is shown here. Okay, it is a two-terminal device, a p-n junction diode, symbolically represented as shown in the figure. So this is the symbolical representation of p-n junction. You don't need to draw this complex diagram, this elaborated diagram every time. You can draw this and you will get full marks for that. Okay, basically that is the meaning. Okay, the direction of arrow indicates the conventional direction of current. Now let me explain what is the meaning of that. So we have a diode. So what will happen, I will explain this after we are discussing about the biasing. So basically this is the P side, this is the N side. Okay, so if you allow a current to flow through the diode, then diode will carry current only from P side to N side, and if you try to flow the current in the opposite side, it will stop. This is a wall. Okay, this is a wall. So if the current tries to come from this side, it will be stopped because of the wall, and if the current is flowing from this side, then it will be allowed pass through this and it will go. Okay, this will help you to remember P side, N side diagrams if you are struggling with the P side, N side, and how you can remember what is the forward biasing, what is the reverse biasing. That will help you to remember if you understand this symbol. This is very easy to remember. Now, p-n junction diode under forward bias. Okay, forward bias, what is the meaning of forward bias? So forward bias means when diode is conducting current. Okay, basically it means that diode is conducting current. So basically diode, you are saying that okay, you are forward bias, you can carry current through it, you are conductor, you are just behaving like a simple conductor. Okay, when an external voltage V is applied across the semiconductor diodes such that P side is connected to the positive terminal of the battery and N side to the negative terminal of the battery, it is said to be forward biased. Okay, so when you connect the P side to the positive of the battery and N side to the negative of the battery, so as the name suggests, P is positive, N is negative. So if you connect them like that, then you will say that the diode is forward biased. The applied voltage mostly drops across the depletion region, and the voltage drop across the P side and N side, the junction is negligible. Okay, so basically the meaning of that is, if you take a p-n junction diode, okay, and if you connect the P side to a positive of the battery and N side to the negative of the battery, okay, then there will be current flowing in the diode. Okay, this is called p-n. So as I said, the current will be allowed to pass, and this is called forward biasing. So the current is flowing in the direction of the arrow. Remember that. You do not consider this to be a triangle or any head kind of a thing. You can consider this to be an arrow. Okay, so arrow means the direction of motion, right? So if you consider this to be an arrow, okay, old-fashioned arrow, then this is the P side and this is the wall. So this is a brick wall. So current will not pass through this side. Current has to pass only from P to N side. This is important. Okay, we will see that. Now, the direction of applied voltage V is opposite to the built-in potential. That is very important. If you remember, there was a built-in depletion potential, depletion voltage, which was actually opposing to the diffusion of the process. So diffusion process was stopped initially after initial mixing. The diffusion process was stopped and drift current took over and they cancelled each other. Now, once you are applying any external voltage, then what will happen? Okay, as a result, the depletion layer width decreases, and the barrier height reduces. So barrier potential reduces. We see that barrier potential, there was a barrier potential because of the negative and positive. So how it will look like? The effective barrier height under forward bias is V minus V naught. So if you see, this is a forward biasing diode. Okay, P side is connected to the positive of the battery, N side is connected to the negative of the battery, and as you are increasing the voltage, okay, barrier potential is slowly decreasing. Okay, barrier potential will decrease, and if you increase the potential long enough, you will see that this depletion region, which was previously it was longer, now it is reduced, it will completely go away and current will flow in the circuit. So for that you have to apply potential voltage which is larger than that of the depletion voltage. So if the depletion voltage, suppose for silicon depletion voltage is 0.67, okay, for example 0.67 volt is the depletion voltage for suppose silicon. Okay, to make it conducting you have to apply external voltage which is greater than 0.67 volt. That is, say suppose you apply 1 volt. Okay, in that case the diode will conduct. For ideal diode, for an ideal diode, this depletion voltage is 0. Okay, so for an ideal diode this depletion voltage is 0. So as soon as you apply a voltage across P side and across N side, it will immediately start conducting. Okay, so this process is for a real diode, but for a ideal diode, okay, for most problems numericals, if we solve any numericals, that will be based on ideal diode unless and until it is mentioned. Okay, if they are giving, for example, if you are solving JEE problems, okay, they have a lot of problems based on actual diodes. Okay, they will mention silicon diode with depletion voltage 0.67, okay, or 0.7. Okay, similarly they will say germanium diode with 0.1 voltage. Okay, so they have, there you have to be careful, but in case of KCET they will not give such cases. Mostly I have not seen any questions based on the depletion voltage. They will mention directly this is an ideal diode, consider this is an ideal diode. Okay, we'll solve the numericals tomorrow, then you will see. When a P-N junction diode is in forward bias, which type of charge carrier flows in the connecting wire? Very interesting question. Okay, so they have given you ions, protons, holes, free electrons. Remember that no matter what is the type of circuit, only one thing that flows in the circuit, that is free electrons. Free electrons only flow in the circuit. It does not matter, okay, whether it is forward bias, what is reverse bias. Okay, free electrons are the majority carriers. There will be holes moving in the circuit, but holes are also motion of the electrons. You remember that holes are moving in the direction of the electric field, applied external electric field, but they are also motion of electrons. Electrons are moving opposite direction, right? So that is the main thing. Okay, even though holes are moving, holes are not major thing, electrons are the major thing which making the holes move. Let us look into semiconductor diode in reverse bias condition. So in reverse bias condition means when you connect the inside with the positive, okay, and negative side with the positive. So whatever their name suggests, you are doing the exactly opposite. Okay, so positive with negative and negative with positive, that is the reverse bias. Okay, in case of reverse bias, what happens when an external voltage V is applied to across the diode such that N side is positive and P side is negative, it is said to be reverse bias. And in reverse bias, current does not flow. The very small amount of current flows usually, and the width of the depletion region increases. So this becomes very hard for electrons to cross this depletion region and the current flow stops in the circuit. Okay, the direction of applied voltage is same as the direction of barrier potential. So the barrier height increases and the depletion region widens due to the change in the electric field. Okay, so the effective barrier height under reverse bias is V plus V naught. So barrier potential slowly increases. Barrier means the wall. Okay, so if you want to cross from one side to another, if the wall is, if there is no wall, it will be easier for you to cross. But if there is a wall long enough, then you will not be able to jump, right? Similarly for electrons, if the barrier potential is high enough, they will not be able to move from N to P. Okay, so basically what you are trying, you are making N side positive and P side positive negative, and you are saying you cannot go there. Okay, so they are being stopped from moving, and if you plot the graph of P-N junction, then you will get this kind of graph. Okay, this is called IV characteristic graph. This graph is also not completely part of the syllabus, only the graph structure. Maybe they will ask you some, they will give you some diagrams as they ask diagram based question, and they will say which one representing the forward bias. Okay, so as you can see that in forward bias, this is the forward bias. Okay, this is the forward bias. Okay, V is positive, and if the V is negative, this is the reverse bias. Okay, this is reverse bias, this is forward biased, right? Now, in forward bias, what happens is, as you are increasing the voltage, the current is slowly increasing. For silicon, they have taken the value for 0.6. So, initially, there is no current. Why initially there is no current? Because they have to overcome the barrier potential. If the applied voltage is less than the barrier potential, there will be no current in the circuit. This is also a very important point. You should remember that. Okay, if the applied voltage that you are applying, even the diode is in forward bias, if the applied voltage is less than that of the barrier potential, there will be no current in the circuit. That's why there is a 0 here. Okay, now as you are increasing the voltage anymore further, okay, current will suddenly increase many-fold. As you can see, this is a non-ohmic conductor. In ohmic conductor, if you remember, in ohmic conductor the graph was like this. Okay, it was starting from 0 and it was going in a straight line, right? So it is not going in a straight line, it is going in a curved way. You can find the dynamic resistance. There are ways to calculate that. I am not going into that detailed dynamic resistance, etc. And similarly, when you are doing the reverse bias, okay, something interesting happens. So initially the current is low, as expected. The initial current is very, very low. Also, it is in micrometer. If you see, the graph is in micrometer range. Okay, after some time at very high voltage, okay, very high reverse voltage, if you see this current, this is happening at 0.6, then 0.8, 0.1. If you see, the range is also small. But in this case, if you see 20 volt, minus 20 volt, minus 40 volt, minus 60 volt, so around minus 80 and 100, that is minus 90 volt, the reverse current suddenly increases. Okay, this is called a breakdown voltage. Diode is in breakdown condition. So it's completely broke down and there is a sudden increase in the current, and that is very interesting thing happens, and that part is not part of the syllabus also, but you should remember this is called breakdown. Okay, there are two types of breakdown: avalanche breakdown, Zener breakdown. Zener diode used to be in your syllabus, but that is no longer part of the syllabus. So if you find any questions related to Zener diode, you don't need to solve it for KCET exam. Now, let us look into the application of junction diode as rectifier. So junction diode, as we have learned, what is the use of it? Okay, so you charge your mobile, right? You charge your mobile using a charger. Have you ever wondered what is the basic composition inside the charger? So basic composition inside the charger can be a simple diode. It is not simple diode, it is a little bit complicated diode, but at the core, at the heart of the charger is basically a diode. Okay, now what is it doing? You know, your mobile phone is charged using your mobile phone has a plus and minus battery inside it, right? So that is a DC source, right? Your mobile phone runs on a DC source, but the supply that is coming to your home, that is an AC source. We have discussed about AC and DC in our alternating current chapter. So now how can you charge your DC mobile phone using an AC source? Not possible. Normally it is not possible. Okay, it will not function. Even your phone will break down. That is why we need a charger. Charger bridges the gap of the supply voltage which is in AC and the receiver which works on DC. So that converts the AC voltage into DC voltage. That is the basic function of a charger. Okay, now why that is happening, how this is happening, that is called a rectifier. Rectifier basically converts AC to DC. That is the basic function of a rectifier. Now, in a diode, you have two basic rectifiers. One is a single wave rectifier, okay, and then there will be full wave rectifier. This is half wave rectifier. It rectifies only the upper halves. This half is rectified, this half is cancelled, okay, and this half is rectified, this half is cancelled. So this is a half wave rectifier. Okay, half wave rectifier, only one half is rectifying. Okay, and if you consider the frequency of the input voltage, suppose the input voltage has a frequency f, then output voltage will also have a frequency f. as you can see, the frequency of the output voltage will also be f after f seconds. So for input voltage, this is the one wave. Okay, for output voltage, this is one wave. Okay, so for after f seconds, it is appearing 1 and 1. So you can say if the input frequency is f, output frequency will be also f. This is input. This is input voltage. You are inserting the this transformer through this transformer. You are inserting an AC to the diode. Okay, and the diode is converting this into a DC voltage. So you are collecting this. This is your plug output. Okay, that is your C port that you are inserting in your mobile. Okay, this is the C port which you are inserting in your mobile. Just for example, and inside that there is a transformer from which the power is being transferred, and then there is a diode inside the your charger. But it is not as simple as that. There is a lot of different components as are involved as well, and the diode is not simple. It can be a Zener diode. Okay, obviously the core part is a Zener diode. Zener diode is a very interesting thing that is used to convert voltage. Okay, maintain voltage, and as well as somewhat rectification. Rectification is not important for Zener diode, but it maintains a voltage. Okay, but the main core, the chip that is used, the chip has a lot of diodes, and each of the diode is converting a part of the input signal. That is how it works. Okay. Now there is one more rectifier, which is full wave rectifier, and full wave circuit is in the full wave rectifier we are using two diodes. Okay, so in half wave rectifier, let me explain the process a little bit. I think that will helpful. Okay, so first of all, when the current is increasing in the circuit in the input, so basically what is happening, you are applying this voltage. Okay, so when you are applying this voltage, what is happening, this side is positive, this side is negative, right? So basically your P side is positive and your N side is negative. So what is the biasing? This is a forward bias, right? So in forward bias, diode conducts. So diode conducts and you are getting an output voltage. Okay. Now when it is in the second phase, that is in this phase, okay, this phase. Now what is happening? Now this side is now positive and this side has become negative. Okay, now because it is going down, current is decreasing, that means this upper side is now negative and below side is now positive. So basically N side is positive now and P side is negative. So N side is positive, P side is negative, that is a reverse bias. So no current flows in the opposite direction. So in this direction no current flows and you get a blank. Okay, so when you are connecting current from here, you are getting a blank here. Okay, so as you can see, this is not very effective because you are losing out lot of energy. Even though you are inserting the full energy, you are only getting half of the work done. So the meaning of that, you went to a shop and you want to buy, say, a packet of milk. Okay, or suppose you want to buy a iPhone 16 Pro. Okay, you want to buy an iPhone 16 Pro, you went to the shop and you have to, if you buy one 16 Pro, the shopkeeper asks you, you have to pay for 2, then only I will give you 1. Is it a good deal or bad deal? Obviously bad deal. You can buy one iPhone Pro using only one's money, right? If the shopkeeper says, no, this is very costly, you have to give me price of 2, then only I can give you 1. Which is a bad deal, obviously, right? So here it is happening like that. You are paying for 2 iPhones, but you are getting only 1 iPhone, which is not very useful, right? So they have come up with a new idea that is called full wave rectifier. So what is a full wave rectifier? Full wave rectifier involves 2 diodes. So during the first cycle, when the cycle is like this, so this is positive and this is common. So you can consider this is a common. So this side is positive and this side is negative. Okay, so in this case what happens, this diode has P with positive and N connected with ground, so the current will flow in this case. Okay, so in the first half cycle, current, this diode is conducting, whereas in the next half cycle, this is now positive and this is negative, right? So in this case, this diode will have a P positive and N negative. Okay, and that diode will have N positive, P negative, so it will not conduct. So first half cycle, this is silent, only this diode is conducting, and in the second half cycle, this diode is conducting and this diode is silent. And if you observe, the direction of current through the RL is now in the same direction. Okay, so where here the current is changing the direction. Once it is flowing in this direction, another cycle it is going in this direction, but output we are getting the current in only in one direction. So that is why it is called a full wave rectifier. So they are able to convert an AC into a DC. Okay, and if you see the graph of the full wave rectifier is given like this, and if the frequency of input is F, then frequency of output is 2F now. This is interesting. Okay, now you can consider this as an individual wave, and this is another wave, this is another wave, this is another wave. So if the frequency of input is F, then frequency of output in case of full wave rectifier is 2F. Okay. Now let's see one question. A full wave rectifier with diodes D1 and D2 is used to rectify 50 Hz alternating voltage. Okay, and the diode D1 conducts dash number of times in 1 second. So what is the meaning of 50 Hz? 50 Hz means it is 50 cycles per second, right? So 50 cycles per second means it is giving you 50 top and 50 bottom each second. Okay, so this is one cycle. Okay, now 50 Hz means you are getting 50 of these and 50 of these in each cycle. Right, now they have asked you how many times the diode D1, only the top diode. If you remember the circuit in the previous case, how many times the diode D1 conducts in each second. So obviously diode D1 will conduct whenever this is flowing in the circuit, right? So how many times this top is flowing, the peak is flowing 50 times. So diode D1 will conduct for 50 times. So correct answer is 50. Okay, and if they ask you how many times diode D2 will conduct, then diode D2 will conduct for this cycle. So diode D2 will conduct again 50 times. Okay, but eventually they are reversing this voltage from top to bottom, right? Now if you want the entire series available to your fingertips, what you have to do, you have to visit our channel, you have to go to the playlist section, find this KCET 2025 Physics playlist and bookmark it. Okay, if you bookmark it, whenever we are uploading a new video, it will be available to you. You can watch at your own time, but don't fall behind, don't create a lot of backlogs. That will only prevent you from achieving your goal. So I wish that you are watching my video as soon as it is getting published. And also for KPL, you have to join our WhatsApp group, and the link is given in the description. If you like this video, don't forget to like it with your friends and share with your friends, and please subscribe to our channel if you have not yet subscribed. Thank you very much. I'll be back with semiconductor diode PYQs tomorrow.